Hello, 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 everybody, and welcome back. We're on our second last question of the 2010 Fermat paper. We are looking at question 24. Spheres can be stacked to form a tetrahedron by using triangular layers of spheres, which we have pictures of here. We create a big pyramid here. Each sphere touches the three spheres below it. The diagram shows a tetrahedron with 4 layers and the layers of such a tetrahedron, so we separated out the 4 layers. An internal sphere in the tetrahedron is a sphere that touches exactly 3 spheres in the layer above it. So every sphere touches the 3 below it, but for example, here's the first internal sphere that touches the 3 directly above it. Okay. For example, this one here, not an internal sphere, it just touches that one. It doesn't touch this one over here, who touches these 2 and this one. Okay. For example, there is one internal sphere in this fourth layer. Okay, I already jumped ahead to explaining that when they were going to. But no internal spheres in the first 3 layers. A tetrahedron of spheres is formed with 13 layers, and each sphere has a number written on it. Okay, what number? The top sphere has a 1 written on it, and each of the other spheres has written on it the number equal to the sum of the numbers in the spheres in the layer above it with which it is in contact. Okay. This is sounding like Pascal's tetrahedron, which is a generalization of Pascal's triangle, which is nifty, but not something necessarily everyone will have seen or heard of. But if you know what Pascal's triangle is, they're making not a triangle version, but sort of a tetrahedron version here. Okay. For the whole 13-layer tetrahedron, the sum of all the numbers on the internal spheres is. Okay. So let's break it down for a moment. So we got 13 layers. Fine. I think 13 is probably an arbitrary choice. We're going to need to start figuring out numbers. Maybe not every individual number, although I will either at the start or at the end briefly talk about Pascal's tetrahedron, because it is something I'm familiar with. But I'll try not to use that in the actual solution that I'm presenting here. So we need to figure out numbers, but we also need to figure out what the internal spheres are. Where are they? How do we get them? How many are there? Okay. So that's sort of the plan. Figure out what the internal spheres are, and then what numbers are on them. And we want the sum of all the numbers on the internal spheres. Now, that's one way to do it, but we could flip it around, figure out the total sum of all the numbers, and subtract off we could call them external spheres, the ones that aren't internal. And that might be something that's easier to calculate. So we'll have to think about that. We're going to explore for a little bit here. Now, since I mentioned Pascal's tetrahedron, I'll just briefly talk about Pascal's triangle. Pascal's triangle is a similar sort of thing where you could get, say, circles. Because they use spheres, we'll use circles. And each circle touches the 2 below it, and then you get these internal ones like this 2 that touch the 2 above it. I'm running out of space here. I'll do it in the little notepad that we always have. 1, 1, 1. And these 1s carry off along the sides, just like I suspect the ones will continue along the outsides of our tetrahedron. But you get 1, 3, 3, 1. I'm going to drop the circles just to make it a little clearer. Then 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and things like that. And so in this case, the internal circles would be the ones here, and we'd be subtracting off just a ton of 1s. But there are some nice things about Pascal's triangle. For example, if you're familiar with binomial coefficients, the first row is the number of ways. With 0 objects, you can choose 0 of them. Then you get 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2. If you're not familiar with any of this notation, just wait for a moment. I'll be done in just a moment. Now, for the tetrahedron, the Pascal's tetrahedron, let me get another circle behind there, or a sphere behind there. You get a similar sort of thing, except the numbers that you're going to get are... So you get 0, choose 3 zeros, and then on the next layer you're going to get 1, choose 1, 0, 0. You're going to get, rather than binomials, which can technically be written as 0, choose 0, and 0, separating into two groups. So I've got 0 numbers, I separate them into two groups of size 0. And the ones are 1, choose 1 to go in one group, 0 to go in the other group, or 0 to go in the first group and 1 to go in the next group. And you get these binomials. Well, here you get trinomials. And so you'll get 3 numbers on the next layer. And then for the layer after that, it'll be 2, and you get 2 choose 0, 0. And 2 choose, you could have 1, 1, 0, and you'll get 6 ways to do this, and that'll give you the 6 spheres on that layer. And there's some nice properties. For example, every row of Pascal's triangle adds up to a power of 2. Every layer, I guess, in our tetrahedron will add up to powers of 3. We'll see if we can come up with that organically, because that would be possibly a nice result. But it's just something nice to know if you're interested in these things or would like a better explanation, because I kind of went through that quickly. You might look up multinomial notation. Okay, it's similar to binomial notation, and it's something that comes up, say, in a finite math course or a discrete math course in university. They're nifty. Anyway, let's get back to the question at hand. I'm just going to take a look at the first few layers. So the first layer has just a 1 in it. I'm going to give myself more space. I don't want to be crammed off to the left here. So first layer is just a sphere. I'm going to look at it from top down. So we get a 1. Second layer, you're going to get... There's going to be too many circles, and my circles when I'm rushing don't go so well. Plus, I think the way the pen works in this program, it's designed to sort of link itself up if I don't draw too far away. So we get a 1, a 1, a 1, and a 1. For the third layer, you'll get, between these two 1s, you'll get a 2. And then you'll get 1s on the outside, and then a 2, and a 2, and a 1. I'm just going to very gently try and draw my spheres. For the fourth layer, we'll get... I'll put in the numbers, then I'll draw the circles. I think that'll go well. You'll get 1s off in the corners again. Between the 1 and the 2, you'll get a 3. Between the 2 and the 1, you'll get a 3. 3 and 3 and 3 and 3. Now you're going to get a middle one here, and it's going to be 6 because it's the sum of each of these 2's. Remember, each one is the sum of the 3 above it. Or, the sum of the 1's above it, because sometimes there aren't 3. So there we go. We start to understand the layer. Now, something that immediately draws my eye is look at the outsides here. I get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So if I was just looking at the side of, you know what? We can... Rubik's Cubes, or I guess Rubik's tetrahedrons. But if tetrahedron. But if I just look at it head on, my spheres, these aren't spheres, would be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. I'd be looking at a face that just looks like Pascal's triangle. So that's an interesting pattern to notice. Now that 6 in the middle, that internal sphere 6, we'll have to deal with him in a moment. But I understand the outside, the external spheres a little bit better. They're Pascal's triangle. There's a Pascal's triangle on this side, and on this side. Now, I can't just sort of add up a bunch of stuff and subtract off, say, 3 copies of Pascal's triangle, because there's overlap. The faces are Pascal's triangle, but the edges, which will have a sphere for each layer, are in common, so I don't want to subtract off too much. I don't want to subtract off a 1 for, I don't want this face to subtract off a 1 in this sphere, but also use this face and subtract off the same one. Then I'm getting into what's called double counting. So we have to be a little careful, and I think this question is going to turn into inclusion and exclusion. But I definitely think that we're going to be figuring out the total of all the spheres and then subtracting off copies of Pascal's triangle, and then adding on copies of, we might call it Pascal's edge, and then we'll probably have to deal with this point here as well, or something like that. We're going to have to be careful, but I think it's just going to be an inclusion-exclusion problem. Okay, So if that's my current plan of attack, if I understand, okay, Pascal's triangle on the faces, and this is true, but I've sort of tried to come about it organically, because I don't ever want to use the fact that I know a lot of math from beyond high school to influence doing math high school level contests. That seems pointless and not very much help for you guys. So I've developed it organically, even though I sort of knew that as soon as I said Pascal's tetrahedron. Okay, so what we're going to do is we're going to get the sum of all spheres, and then subtract off 3 copies of Pascal's triangle, and then we will have double counted some of the edges. I think we have to add on each edge twice, because each edge is counted by our Pascal triangles. So add on 3 Pascal edges, and then I think that top point again, as I say. But okay, before we move on to our actual calculation, let's see if we can figure out the sum of all the spheres. Okay, and also, is this the correct way to think about this? Well, let's do the 5th layer as well. So we'll get 1, 4, 6, 4, 1. I just want to make absolute certain that I'm understanding the problem and the internal spheres correctly. So these are the Pascal triangle parts that will be cut off, and then what's left inside will be, what was the previous layer? It was 1, 3, 3, 1, 3, 3, 1, 6, 3, 3. So we'll get a 12 here, a 12 here, and a 12 here. Yeah. And those are internal ones as well. They're not part of the outside edge. So okay, we are counting up the right thing with this sort of pseudo calculation. All right, so sum of all the spheres. Well, I've got a few of the layers. We can play around with the layers. So I notice the sum of the first layer is 1, the sum of the next layer is 3, the sum of the next layer is 9, the sum of the next layer is 1, 3, 3, 1, so that's 8. And then I don't get another 8 down here or another 8 off here because I've already counted the ones twice. Or I will be counting the ones twice. So maybe I'll say 1, 3, 3 is 7, 1, 3, 3 is another 7, 1, 3, 3 is another 7. So that's 21, and then 6 is 27. So we can sort of realize sums are going to be powers of 3. And we can double check that also works here. 1, 4, 6, 4 here is going to be 15. So I'll get another 15 here and another 15 here. And then I get 36 in the middle, so I get 3 times 15 plus 36. So that's 45 plus 36, and that is in fact 81. So we can notice our pattern. Nth layer sum is 3 to the n minus 1 if you go with their counting method and say it's the first layer rather than what would traditionally be done, which is call it the 0th layer. Like you do in Pascal's triangle, the first line is the 0th line, not the first line. Okay, so with 13 layers, we get a sum of 1 plus 3 plus 9 plus 27, all the way up to 13 to the 12. So I need to figure out how to add this up. Well, it's a geometric series, so it's not the hardest thing to add up. For a geometric series that look like A times R, A times R times R, A times R times R times R, and so on, if we go up to a certain amount, A times R to the K, the sum here is always A R to the K plus 1 minus 1 divided by R minus 1. That's always the sum. So what's our first term? It's 1. And what's our common ratio, the thing we multiply each term by? It's 3. So we've got multiply by 3 once, twice, so we'll go up to 12 times. So 3 to the 13 minus 1 over 3 minus 1. So 3 to the 13 is, just grabbing my calculator because I don't know that one off the top of my head, 1, 5, 9, 4, 3, 2, 3. We want to subtract 1 and divide by 2. 3 minus 1 is 2. So we get 797161. Okay, now that's all the spheres without the external ones, the ones that aren't internal, taken away. How does this compare to any of our potential answers? Okay, we're looking all right. The number that I've got on my calculator is bigger than these, which is good, but it's not so much bigger. Everyone's sort of in the 700 millions. Okay, we're about 20,000 more than any of the other ones, but that's okay. We can work with that. All right, so that's all the spheres, but now I need to take off 3 copies of Pascal's triangle. Well, I've got 13 rows of Pascal's triangle here. And if we sort of employ the same reasoning we did before, just adding up layer by layer, we notice, oh, these are powers of 2. This is also something that you might already know if you've ever explored Pascal's triangle. So we've got the same sort of summing thing that we need to do. So we'll get 2 to the 13 minus 1 over 2 minus 1. And 2 to the 13 is, I want to say 4096. Ah, rats, I was close. So 8192, subtract 1, divide by 1, 8191. Okay. So we'll have whatever 700-something thousand we had, minus 3 copies of this. All right, here's where I need to be careful. So I'm going to, I don't know what the best way to do this is. It's inclusion and exclusion, and I have to make sure that I'm including the right things. So here I'm doing a little top-down picture of my spheres. I think that's probably enough. Okay. So we get what was it? 3 to the 13 minus 1 divide by 2. So that's 7, 9. Oh, let's get a color like I was trying to do a second ago. Let's say 797161, and that's all the spheres, everything. Actually, let's keep that one in black, because that's the way I drew my spheres. Okay. 797161. Now I want to take away 1 copy of Pascal's triangle. That's, let's say, the purple side here. So that's minus 1 copy of 8191. And then we take off another side, but you'll notice that some of these are being taken off again. But that's another copy, 8191. And then let's say the orange side, which again is taking away some that have already been counted amongst the purples. And some that have been counted amongst the blues. Okay. So we have taken off each of these purples, taken off each of these blues, and we keep going. But we've taken off this sphere that's both purple and blue twice, so we have to add him back in. So we have to add each one of these ones back in. How many of those are there? Well, 13 layers. We start at the top, so we'll have 13 of these, let's say, green edge ones that have to be added back in. So we add back in 13 of those because we took off 2 copies of that sphere when we only wanted to get rid of 1. Using yellow, we add in this edge again, so we add on 13. And then let's use the magenta. This edge over here, we add it back in. Okay, now we've dealt with all of those, but what happened to this top one? That's crazy stuff. Okay, so we added it once, took it away, took it away, took it away. So now we owe 2 copies of this sphere. Then we added it again, now we've broken even. but then we've added it again, so we need to take it away one last time. All right? Got to be very careful, make sure the reasoning is sound. I added him in. We don't want to ultimately count him. So we needed to get rid of him. We got rid of him. Then we got rid of him 2 more times. So now we owe 2 copies. We pay back 2 copies, but then we paid a 3rd copy. We don't want this one included. So actually, let's, instead of using check marks to say I've cleared things away, let's say added it in, got rid of it, added it in. So I need to get rid of it once more. So I need to subtract 1, as we've done. So if I do this calculation, so minus 3 copies of 8191, add on 3 copies of 13 for the edges, the Pascal's edges, which aren't very interesting, and then subtract off 1 for that point at the top who's been used so many times, we get 772626. And I'm saying that's my answer. Now let's see, is that a possibility? I'm looking for 2626 right there at the end. And just to make sure my inclusion-exclusion didn't foul up, are any numbers even close to this? No. No, they're not, so I am very confident in my answer of E. And that finishes up question number 24. Probably would have gone a little quicker if you knew things like Pascal's tetrahedron, but really, it's sort of a 1 in 1,000 shot if the concept that appears in questions 23 or 24 or 25 are something you've actually seen before. So we want to not sort of just read math books every day, all day, although if you want to, go ahead. But we want to build up our reasoning skills. So I sort of tried to ignore my prior knowledge of this stuff and said, okay, let's create a plan of attack. Let's create a way to add these things up and subtract, and we also noticed things like the ones that we didn't want to count formed Pascal's triangle. Powers of 2 for the rows there. That might lead us into powers of 3 for the layers of the tetrahedron, and then it becomes a very, very quick inclusion-exclusion. But we still had to be careful. Okay. If you're interested in this stuff, as I say, you can look up multinomials. You can also, I'm pretty sure, look up what's called Pascal's simplex, which is an n-dimensional version of this, but it's not particularly interesting for math contests because they wouldn't even be able to show us layers of 4-dimensional spheres. And anyway, that's for you to look up if you're interested in. If you had a different way of doing the question, I would absolutely love to hear it, so you can leave a comment below. Don't forget, you're always welcome to like or subscribe. It just shows support for the channel. But either way, we're going to finish off our Fermat paper in the next video with question number 25. I'll see you there. Take care.